Okay, now we will finish the discussion about the ideal gas. We will determine the macroscopic quantity belong to the ideal gas. Based on the partition function we have derived previously, starting from the energy of one particle inside the assembly, and then calculating the partition function of one particle. And then we have finally obtained the partition function of gas assembly of ideal gas. So we have calculate partition assembly of ideal gas, of an ideal gas, has a partition function is larger equals to v power n of a 3 power n, and then this 2 pi m k t, this is of a 3 n of a 3. This is the partition function of an assembly of ideal gas. We have derived this one, and from this partition function we are going to determine the macroscopic properties of the ideal gas. First, we will calculate the Helmholtz energy, Helmholtz free energy. We have discussed, we have learned that the Helmholtz free energy is given by minus kT ln Z. Minus kT ln Z, and Z is this one. So the Helmholtz free energy becomes minus kT, and we take the natural logarithmic of this one. Natural logarithmic of v power n of h power 3n 2 pi m k t power 3 of 3n of 2, and then minus kt. We separated this one ln vn. This is become n ln v, n ln v, and then plus ln 1 of a power 3n, and then plus 3n of 2 ln 2 pi m k t. This is the Helmholtz free energy of our gas, our ideal gas. So it depends on the volume and the temperature of the gas. Now the important parameter is the equation of gas, equation of state. We have also discussed in a previous lecture that the pressure can be derived from the Helmholtz free energy based on the equation pressure equals to minus Helmholtz free energy partial derivative of the Helmholtz energy against volume. So we can determine the pressure of the system of the assembly by deriving the Helmholtz energy respect to the volume. Now we have here that the free energy, Helmholtz free energy, depends on volume only in this term. So if we derive this Helmholtz free energy, this is minus, this become kT, and we derive against volume, this is n, derivation against volume become 1 over v, and this is because this term does not contain volume, this is become 0 and 0. So we can then obtain the result is n k t over v. Or we then have the equation of state for the ideal gas. Ideal gas becomes PV equals to NKT. This is the expression, the well-known expression we have studied in thermodynamics and thermal physics and another lecturer in undergraduate. So this is the well-known equation for an ideal gas And we have derived this well-known expression using our approach by starting from the partition function of particle and then partition function of assembly, and then Helmholtz free energy is developed, is right, it's obtained, and then derivation of Helmholtz energy against the volume. We will finally obtain the very, very known expression for the ideal gas. We have studied here from the undergraduate lecture. So our approach can give exactly the same results for the ideal gas state. Next, we will calculate the energy of an ideal gas. Energy. Energy of assembly of ideal gas. We have also learned that the energy is expressed as K T squared dou of dou T ln Z. So the derivation is performed against temperature. For pressure, we obtain the pressure by derivation of Helmholtz energy against volume. Now look at this expression. This is ln Z, natural logarithm of the assembly partition function. So we will use this expression here. Okay. Now, if we look at this expression, we don't use this one. If we look at this expression, because we will derive against temperature, we are looking for the term that contains temperature. Here, no temperature, they will become zero. No temperature become zero, and temperature is here. Now we can separate this expression to become 3n over 2, and then ln 3 pmk plus ln T. So I separated the temperature ln, and another, the constant is a group. We group the constant in one term. So if we derive this expression against temperature, we will only leave this one. This will become zero also. This only this one. So the energy of the assembly become KT squared. We only derive this expression 2n over 2 d over dt ln t. So, sorry. D over dt 3n over 2 ln t. Ln t. We only consider the last expression that contains temperature. So if we do this one, Et 3n over 2, if we derive ln is equal to 1 over t. So we obtain t squared, this is over t, then 3 over 2 n kt. And we can only write this 3 over 2, n over na is Avogadro, and Avogadro the multiplied by Boltzmann constant, and this one the mole, and this one this universal gas constant. We finally obtain 3 over 2 nRT. Now this is the well-known expression for the energy of ideal gas in a three-dimensional assembly. This is very well known. We have used this expression in the lecture of thermodynamics at the undergraduate level. So we have obtained for ideal gas the expression of the formulation, the method of canonical assembly give the same result as we have learned in thermodynamics or at another lectures in undergraduate level. Now finally, we will determine what is the heat capacity of an ideal gas. Heat capacity. It is very simple. Heat capacity is the derivation of energy against the temperature. We use this one. This becomes 3 over 2 and so this is the heat capacity of ideal gas. We have also learned this in undergraduate level. So we conclude here that using the concept of canonical assembly, we will obtain many expression of any kinds of assembly in which the number of particles remains constant, but the energy is permitted to moving inside the assembly or to move out from the assembly to the surrounding. But specifically in case of ideal gas, we obtain the well-known expression that we have learned in the undergraduate level. So, especially when applied to the ideal gas, we extract the similar equation as we have discussed in another lecture in undergraduate or even in high school. But the concept of canonical assembly can be extracted, can be extended to any other assembly. So we can only obtain the macroscopic expression for energy, for pressure, and for other thermodynamical quantities of the assembly. Next, we will discuss if the gas is not an ideal gas. That means that there is interaction between gas particle and the interaction energy cannot be ignored compared to the kinetic energy. So the energy of the gas contains the kinetic terms and the potential terms. How to obtain the expression for the states of such gas? If both energy are comparable, if the kinetic and potential energy are comparable, we expect that the expression should be different from the expression for the ideal gas. We will discuss in next meeting example of gas assembly containing interaction between particles. What is the expression for the states? And we will show that the expression will be similar to the equation of Van der Waals gas. So Van der Waals gas is the modification of ideal gas by reconsidering the interaction between gas particle and the volume of a particle gas, the total volume of a gas particle that has been omitted in the development of the ideal gas theory. Thank you.